Hello wonderful person, this is Anton, and you're looking at Europa, a satellite of Jupiter. A nice world that has a beautiful ocean underneath all of this ice shell. Now, once upon a time, our Earth was very similar to this, and in today's video you're going to discover about one such event that may actually occur one day yet again. Anyway, welcome to What the Math. So Europa is actually a very fascinating satellite that we want to visit one day because we're like 100% or 99.9% certain that underneath all of this ice lies a very huge ocean world that we can actually discover in Universe Sandbox by warming this object up through the collisions with various asteroids. So if I collide enough of these things into this moon, you'll see that the ocean will start melting and you'll actually get to see what it all looks like. And it looks like it's going to melt any second now. There's a bit of a mission going on because I did place the sun here just to warm things up a little bit. But I think in a few seconds it's going to turn into a liquid moon. And here we go, the water world. Now, why are we talking about this? Well, very simply, this is actually what may happen and what has definitely happened to our beautiful planet Earth as well. Let's actually go into the Earth simulation. And there it is. And just take a look at it for a second, because what we're going to do is we're going to turn this beautiful planet Earth into an ice ball. And we're going to simulate what has actually happened at least 4 times in history. And possibly will happen again. And one of the most famous events occurred about 717 million years ago and essentially turned our beautiful planet into a giant snowball. Now, what happened and how did it happen? Well, today we're going to recreate this using Universe Sandbox. Now, first of all, what actually causes the temperature to fluctuate on our planet Earth? There's many factors. I've discussed many of them in my CO2 series, where I talked about various effects of carbon dioxide. And you may have found out that, well, there's things like composition of atmosphere. So in other words, atmospheric composition that would be under greenhouse gases. So things like, for example, water vapor or carbon dioxide, or even things like aerosols will actually influence the temperature either by increasing it or decreasing it. There's also the actual tilt of the planet. So in other words, how the planet spins affects what parts of Earth receive the sunlight. And this will in turn change what and how much of sunlight is reflected and what and how much of sunlight is absorbed and what the actual temperature of Earth is. The amount of clouds and the amount of ice on the planet also affects what's known as albedo. This is how much light is reflected. So currently about 32% of light is reflected back into space, whereas about 78% is absorbed by the planet. If the planet becomes more white, this will increase up to about 60%. In other words, not as much warmth will be received from the sun. Other factors are related to the actual orbit as well. So we know that the orbit around planet Earth is not entirely circular. It's actually about 2% elliptical. So the eccentricity here is 2%. So at some point, specifically in December and January, our planet Earth is a little bit closer to the sun, and then it's a little bit farther away in July. This also kind of influences the temperature a little bit. And of course, the solar events. So the sun itself does change with time. And so various solar activities will also affect the temperature as well. There's a lot of other factors, but today we're going to look at one major factor that caused that snowball effect about 717 million years ago. And that specific event actually occurred at least twice or maybe even 3 times in the last 150 years, and I've talked about these previously in the CO2 video, and these are of course the volcanic eruptions, huge volcanic eruptions. The biggest one in the last 150 years was in the region that you're going to see in a few seconds. Now, this particular volcano, known as Krakatoa, is located in Indonesia, somewhere right here-ish. And the eruption in the late 1800s basically covered most of the world in silicate aerosols, which are known for being able to decrease the temperature of our planet Earth. Now, here's actually a graph that I showed you in one of the previous videos that shows you there were 3 such dips in temperature in the last 150 years, and these 3 are actually really big volcanic eruptions. The left one is the Krakatoa, and this influenced the planet quite dramatically for at least 5 years. The temperature was so low that many countries in Europe struggled with producing food, and it caused famine in Russia, in Germany, in Ireland, which by itself actually caused the migration to the United States. So this Krakatoa eruption that happened in Indonesia ended up creating United States through immigration of people from other countries. But that was just one eruption. It is actually possible for a series of volcanoes to erupt all at once, specifically if they're located along the ridge of 2 continents, like for example right here in Japan. If this occurs, then a tremendous amount of sulfur dioxide, which is responsible for this cooling, would actually be released into the atmosphere. Sulfur dioxide is an aerosol that is very reflective. It reflects a lot of sunlight, and it prevents solar radiation from ever reaching the surface of the planet. And this might actually happen again. It happened previously and it might happen again. So about 700 million years ago, such an eruption occurred along one of the ridges of continental shelves and released a tremendous amount of sulfur dioxide. And we're going to actually try to recreate this by doing the following. We're going to create a customized Earth system with just the sun in there, and we're basically going to now simulate this sort of eruption. So let's just say that the entire western North and South America, where there is a continental shelf, starts erupting at the same time. So the Californian shelf starts erupting here, and all of the areas here around Chile and Peru start erupting as well. And all of this releases a tremendous amount of CO2. We're going to emulate this by basically launching a bunch of asteroids at those locations on our planet Earth, and okay, a little bit more powerful than I expected. Well, there you go, there are your eruptions. All of this eruptioning is now going to cause a tremendous amount of sulfur dioxide that is going to be released into the atmosphere. Now, because of these eruptions, the planet might actually first warm up a little bit, but not for a very long time, only for possibly like a few weeks or maybe a month. But the sulfur dioxide that is released is going to spread across the entire planet, and we're going to simulate what happens by going in here and essentially reducing the carbon dioxide levels to about like 100. In other words, what normally carbon dioxide does, sulfur dioxide is going to cancel out. Doesn't mean that we should be releasing more of it. It just means that this is how you could potentially mitigate the effect of carbon dioxide if, you know, worse comes to worse. Now, because we've decreased the amount of carbon dioxide, the planet will now not be able to maintain as much heat in there, because basically a lot of stuff is getting reflected. I'll probably even lower this to like a 10 or so. And you can kind of see the leftovers from volcanic eruptions there. But our planet will now start losing temperature. You can kind of see this on the graph here. It will slowly start dipping down into the colder and colder climates, because unfortunately the heat is no longer maintained here. So this is about the actual time is here, so it's about 12 days later, and we've already lost about 1 degree Celsius. So let's see how this goes. Well, I'm actually going to press this button right here, optimal for climate simulations, and we're going to just take a look at our planet as the time passes and as the temperature keeps dropping lower and lower. So after about a month, we've already lost 2 degrees, and you can see winter spreading into actually everywhere. Asia, Middle East, the entire region is already covered in ice slowly. And that's because that sulfur dioxide I released is not letting any more light come to the planet. It basically kind of is bounced off in the same way that it's bounced off Venus. But because Venus has so much CO2 on the surface, the actual warming effect, the greenhouse effect, is counteracted by the reflectivity of Venus. Venus has a tremendously large albedo effect. Its albedo is a lot higher than it is on planet Earth. But even though the albedo is so high, the temperature of Venus is very hot because of the CO2. So, which is what we'll do later on. We're going to release a tremendous amount of CO2 too. Okay, so a year later, the temperature is now about 7 degrees lower than it used to be. You can see that North America is being covered by ice quite fast. There you go. Look how fast this is happening. This is like about a couple of days per second. And so everything that used to be green is now becoming an ice shelf. And there goes Florida in a few seconds. So this only took about a year. And a year later, essentially, this is what we get. Even Northern Africa has ice. All of the Europe is covered in ice already. All of the East Asia is ice. Only India and Southeast Asia is still kind of okay. So is Australia. Antarctica has grown in size a little bit. Let's take a look at the North America. It's going to come out in a few seconds. But as you can see, the temperature is dropping dramatically. So a year and a half later, basically we have what would actually be similar to a smaller ice age. So a little ice age as it's known. Now the ice shelf is retreating, and that's probably because it's actually technically summertime right now. So the northern hemisphere is receiving a little bit more light than it would be otherwise, but the average temperature is still dropping. It's already 12 degrees below. And so we're going to accelerate time a little bit more here. And you'll see that next winter, things will not be so good for most of this region here. And even though it's dark here, chances are even Florida will be covered with ice. We now have ice in most of North Africa. Northwest Africa, that is. And it's now slowly creeping in everywhere else as well. Half of Japan is ice. Oh, surprisingly, South Korea, where I'm located, is not ice yet. But it's slowly getting there. The average world temperature is -3 degrees Celsius. And we're basically getting to the point where, look at the size of Antarctica. It's huge. It's more than doubled in size now. And even releasing a tremendous amount of CO2 at this point will not really help us very much. Even if we actually suddenly start releasing like 10 times more than we are releasing right now, it will not save us. So Antarctica has now joined with South America. Africa is slowly being covered by ice as well. Saudi Arabia is now an ice desert. And only India seems to be still kind of okay. The temperature in India is probably similar to a temperature in North Canada right now. It will probably be kind of chilly in the summer and somewhat cold in the winter. And look at that. South America has just become ice. Africa is ice. Everything is ice. The average world temperature is -15 degrees Celsius. There are still only oceans that are not completely frozen over. So welcome to the Ice Age. It only took about 5 years to get there. And it will not get any better anytime soon. I'm going to accelerate time a little bit more, just so you can see how within the next 5 years, everything is now ice. This is a snowball Earth. The big ice ball, very similar to Europa in a sense. Maybe the actual ice shelf will not be as thick as Europa, but this is essentially what Europa is like. Europa is the satellite of Jupiter that I showed you in the beginning. Now, the thing is, it's very likely that if there's a huge volcanic eruption on Europa, we might be able to see what would happen to this particular moon. Now, the thing is, this didn't last for forever, obviously, because today Earth doesn't look like that. And so another huge volcanic eruption in the next 100 million years caused all of this ice to melt. So this actually lasted for many million years. Over 100 million years. Earth was basically like this. And as a matter of fact, about 25% of the entire life of Earth, in other words, in about over 1 billion years, Earth was covered in large chunks of ice. Not exactly like this, but similar to this. So then the eruptions started to reoccur underneath all of this ice shelf and started to release a tremendous amounts of CO2 now. As a matter of fact, it was because of the CO2 that the Earth warmed up again. So we're going to increase this, let's just say to like, I don't know, maybe 2000 ppmv and see what happens. So you can kind of see that the temperature started to increase a little bit. Maybe not as fast as it was decreasing, but we'll see if this actually helps us. So we're now going to try to change this back into a habitable Earth by essentially re-releasing CO2 and hoping that sulfur dioxide is reabsorbed. And you can see that every year this is actually going higher and higher and higher because of the CO2. So within about 10 years after I started releasing CO2, the temperature is already about 25 degrees warmer. It's slowly climbing up. Now the ice is not melting yet, and due to the very, very high albedo of 60%, it will actually be a lot harder for us to melt the planet. So there needs to be a volcano or something that will melt a chunk of ice, that will actually expose some of the darker parts of the planet for us to absorb more light. Right now we're kind of stuck here. So let's just increase this to about 10,000 ppmv and see if we can actually maybe melt some of the ice and expose some of the planet, and there we go. This actually exposed some of the water. The albedo will now start slowly decreasing. Hopefully. Maybe. Yeah. Here we go. No, albedo is not changing yet, but we're definitely seeing more and more water, which is exposing darker patches of Earth and making planet absorb more light. And every year you can see that the actual ice shelf is retreating. It comes back in the winter, but it retreats again in the summer. Once we're able to melt the planet, we're going to have a huge amount of CO2 in the atmosphere, and the planet will actually be on average a lot warmer than it used to be. And interestingly, this is kind of what happened to our Earth as well. It was actually much, much warmer in the days past, specifically when dinosaurs were around. And it was very likely because of huge amounts of CO2 in the atmosphere and possibly some other greenhouse gases. However, this obviously didn't last, and other ice ages came back. So our planet today is a little bit cooler than it used to be millions of years ago. All right. So 10,000 is not enough. Let's go to 20,000. 20,000 ppmv, that's a lot of carbon dioxide. That's about 50 times as much as we have right now on our planet Earth. We are at about 406 level as of 2017, which is actually much higher than it used to be. It used to be about 280 for like thousands of years, but it is now at 400-ish. Oh, look at that, it's happening, it's happening. The planet is melting, albedo has decreased to original value, and now the temperature is climbing. It's climbing really, really, really high. Let's see how high it gets actually. So this is a post-ice age climate where things will get really, really, really hot due to the huge amounts of CO2. And the only way we can decrease CO2 is through life. So plants and plant-like life will hopefully absorb all of the CO2 and change the temperature, dropping it to manageable levels, because right now it is close to about 50 degrees Celsius. And anyway, so that's essentially the Ice Age history of our planet Earth that happened about 717 million years ago, and actually there are at least 5 such events. And interestingly, scientists think and actually believe quite strongly that today we are actually in the middle of such ice age. It's very likely that our planet will actually be cooling down in the next few thousand years, but due to the huge amounts of CO2 that we released in the last 100 years, it might not happen as quickly as scientists expect. What's going to happen, we'll learn in the future, but for now, all we know is that CO2 and sulfur dioxide are very, very powerful gases that can actually influence our atmosphere quite dramatically. And anyway, that's all I wanted to show you in this video. I wanted to turn our planet Earth into an object similar to Europa. Basically, a nice shelf on top and a huge, humongous ocean underneath. So this is what Europa is. Maybe one day we'll find out if Europa actually does have volcanic eruptions underneath it, and those volcanic eruptions might even uncover the surface for us. So maybe, just maybe, Europa will also become a liquid world, just like our planet Earth. But anyway, hopefully you learned something from this video and you enjoyed watching it, and if you did, don't forget to subscribe and potentially share this video with your friends or someone who enjoys watching space videos, science videos, and video game related education videos. Come back tomorrow to learn something else, something a little bit different, something you may have not known before, and I'll see you guys tomorrow. Space out, and as always, bye bye. And let's actually maybe take another Europa, and just for fun, launch it at our planet Earth. Because, why not? We can do this, right? Why wouldn't you want to launch Europa at what seems to be Africa? Ha, funny. Anyway, I'll see you guys tomorrow. Space out, and as always, bye bye.